Ever noticed how American freight locomotives look like they're only meant to go one direction, while European trains seem ready to roll either way? Today, we're re-uncovering the fascinating engineering story behind why American and European locomotives evolved such dramatically different designs. When you look at a typical American freight locomotive, you'll see a cab positioned at one end with a long hood stretching out in front. The engineer sits up high with a commanding view down the tracks, and the entire machine looks purpose-built to charge forward in a single direction. Now compare that to many European locomotives, where you'll often find a cab at both ends, or a centrally positioned cab that allows the train to operate equally well in either direction. This isn't just a stylistic choice or a random design preference. The story behind these different approaches reveals how geography, economics, and operational needs shape to completely different solutions to moving trains across continents. Let's start by understanding the fundamental difference. A single cab locomotive is exactly what it sounds like. The control cabin is located at one end of the locomotive, typically with a short hood behind the cab and a long hood extending forward. The engineer faces forward, and the locomotive is designed to pull trains primarily in one direction. When the locomotive needs to return or head in the opposite direction, it either gets turned around at a terminal facility, or in some modern operations, another locomotive can be positioned at the other end of the train. European double cab locomotives, on the other hand, feature either two complete cabs at opposite ends of the locomotive, or a single centrally mounted cab with controls that allow operation in both directions. This design philosophy means the locomotive can easily reverse direction without any special infrastructure or additional units. To understand why these designs diverged so dramatically, we need to go back to how railroads developed on both continents. American railroads grew explosively in the 19th century across a massive, sparsely populated landscape. The focus was predominantly on moving enormous quantities of freight across vast distances. Picture the scenario. Raw materials from mines in the western mountains needed to travel thousands of miles to industrial centers in the east. Agricultural products from the heartland needed to reach coastal ports. The entire system evolved around the concept of long-haul operations, with trains departing from origin points and traveling hundreds or even thousands of miles to their destinations. At these destination points, American railroads built extensive terminal facilities. These terminals included features like turntables, which are exactly what they sound like, a section of track that can rotate, allowing a locomotive to be turned around to face the opposite direction. They also built Y-tracks, which are triangular track arrangements that let locomotives reverse direction by making a series of back-and-forth movements. These facilities became standard infrastructure at major rail yards across America. The economic calculation was straightforward. If you're running a locomotive on a route from Chicago to Los Angeles, that locomotive might spend days on that single journey. Spending a few minutes at the terminal to turn the locomotive around was a trivial amount of time compared to the overall trip. The cost of maintaining turntables and Y-tracks at major terminals was far less than the cost of building every locomotive with dual cab capabilities. European rail development followed a different trajectory. The geographic landscape of Europe is characterized by much shorter distances between major cities and a far denser population distribution. Rail networks developed with an emphasis on passenger service, connecting cities that might only be 50 to 200 miles apart. These passenger services needed to run frequently in both directions, often with the same train equipment, making multiple round trips in a single day. Imagine a train running between Paris and Lyon, or between major German cities. That train might make the journey, arrive at the destination, and need to head back within an hour or two. Building turntables at every station, or taking the time to run the locomotive around the train through a Y-track simply wasn't practical. The solution was locomotives that could operate efficiently in either direction, allowing for quick turnarounds and maximum equipment utilization. This passenger-focused development also led to the widespread adoption of push-pull operations in Europe. In a push-pull configuration, the locomotive might be at one end of the train pulling on the outbound journey, then remain at that same end and push the train on the return journey, with the engineer controlling from a cab car at the opposite end. This required locomotives designed to work comfortably in both directions. The post-World War II era cemented these different approaches. American freight railroads were consolidating and investing heavily in diesel-electric technology, specifically optimized for long-haul freight. The focus was on raw pulling power and fuel efficiency over continental distances. European rail systems were being rebuilt and modernized with an emphasis on passenger service, electrification, and operational flexibility. These different priorities reinforced the engineering decisions that had been evolving for decades. Now let's talk about the economic factors in more detail, because this is where the single cab design really makes sense for American operations. A locomotive with a single cab is significantly cheaper to manufacture than a double cab design. You're building fewer controls, fewer windows, less climate control systems, and you need less complex electrical and pneumatic systems. When you're a railroad purchasing hundreds or even thousands of locomotives, these cost savings multiply dramatically. Maintenance costs also favor the single cab design for the way American railroads operate. Fewer components mean fewer things that can break or require regular servicing. A single cab locomotive has one set of engineer controls, one environmental system for the cab, and a simpler overall layout. For operations where the locomotive will spend days between terminal facilities, this simplicity translates directly to lower operating costs. American railroads also made heavy investments in the terminal infrastructure that supports single cab operations. A major classification yard might have multiple turntables and Y tracks, along with fueling facilities, maintenance shops, and crew change locations. Once this infrastructure is in place, the cost of turning locomotives becomes almost negligible compared to the savings from simpler locomotive designs. There's also the question of how American railroads use their locomotive fleets. In long-haul freight operations, it's common to use multiple locomotives together in what's called a syst. You might have 3 or 4 locomotives all connected together at the front of a heavy freight train. These locomotives can be controlled by a single engineer in the lead unit, with the other units operating as remotely controlled slaves. This approach gives tremendous flexibility in power management without requiring double cab capabilities. The technical considerations are equally fascinating. From a visibility standpoint, the American single cab design with the long hood extending forward actually has some disadvantages. The engineer's view is partially obstructed by that long hood, especially on curves. However, American railroads decided this was an acceptable trade-off. The long hood houses essential equipment like the prime mover, electrical systems, and in some designs provides a buffer zone that offers the crew additional protection in certain scenarios. European double cab designs typically offer better visibility in both directions, which is particularly valuable in passenger operations where station platforms and urban environments require careful observation. The ability to see clearly when operating in reverse is essential when you re-pushing passenger cars through condead areas. Aerodynamics plays an interesting role as well. A single cab locomotive with a long hood is essentially optimized for forward motion. The nose can be designed for reduced wind resistance when traveling at speed in the primary direction. European locomotives, needing to operate equally well in both directions, must compromise somewhat on aerodynamic optimization. However, with many European passenger services operating at very high speeds, locomotive designers have become remarkably skilled at creating streamlined designs that work efficiently in both directions. Maintenance access is another technical factor. American single cab designs can dedicate the entire long hood to equipment access, with doors and panels arranged for convenient servicing. Double cab designs need to work maintenance access around 2 cab structures, which can sometimes complicate repairs and routine servicing. It's worth noting that American locomotive design went through an interesting evolution regarding cab position. In the early diesel era, some manufacturers offered locomotives with cabs positioned centrally or with short hoods on both ends. However, over time, the industry standardized around the long hood forward or short hood forward designs with the cab at one end. This standardization was driven by operational experience, showing that for American freight operations, the single cab arrangement was most practical. Modern developments have added some interesting wrinkles to this story. In American commuter rail operations, you'll find many trains using double cab locomotives or cab cars, particularly in push-pull configurations. Services like Metrolink in California, Metra in Chicago, and various East Coast commuter systems use equipment that can operate in both directions because, like their European counterparts, they're running short distances with frequent direction changes. Some American freight operations have also adopted locomotives with improved reverse operation capabilities, though these still aren't true double cab designs. Remote control operations in switching yards sometimes use locomotives that can be controlled from a portable device, allowing a single operator to move the locomotive in either direction from trackside. The development of distributed power units has provided American railroads with another solution that avoids the need for double cab designs. In a distributed power consist, locomotives are positioned at the front, middle, and rear of very long trains. These remote locomotives are controlled electronically from the lead unit. This arrangement provides better train handling and allows for efficient operation without requiring every locomotive to have full bidirectional capabilities. Looking at the broader picture, both design philosophies represent elegant solutions to different problems. American single cab locomotives are optimized for what they do best, pulling massive freight loads across continental distances as efficiently as possible. The infrastructure investments in turntables and Y-tracks at terminals make sense when your operations involve long distances between stops and relatively infrequent direction changes. European double cab designs reflect a different set of priorities: frequent direction changes, passenger-focused operations, and the need for flexibility in shorter distance services. The additional cost and complexity of double cab designs is justified by the operational efficiency gained in their specific service patterns. It's also important to recognize that neither system is inherently superior. Each evolved to meet specific operational requirements shaped by geography, economic factors, and the nature of rail service in their respective regions. An American single cab locomotive would be poorly suited to European passenger operations, and a European double cab design would add unnecessary cost and complexity to American transcontinental freight service. The story of cab design differences teaches us something important about engineering. There's rarely one correct answer to a design challenge. The best solution depends entirely on the specific requirements, constraints, and context of the application. American and European locomotive designers weren't making arbitrary choices. They were solving real problems with thoughtful engineering that considered costs, operations, maintenance, and the existing infrastructure they had to work within. As rail technology continues to evolve, we're seeing some convergence in certain applications. High-speed rail projects in various countries tend to use train sets with cabs at both ends, regardless of location. Urban rail and commuter services globally are adopting similar solutions because they face similar operational requirements. However, in heavy freight operations, the fundamental differences remain. American freight locomotives continue to use predominantly single cab designs because the operational model hasn't changed. Long distances, heavy loads, and terminal facilities equipped to handle locomotive turnarounds. European freight has been adopting some American practices, but the existing infrastructure and operational patterns still favor more flexible designs. The next time you see a locomotive, whether it's an American freight unit with its distinctive single cab or a European design with dual capabilities, you'll know that what you're looking at is the result of more than a century of engineering evolution, shaped by geography, economics, and the specific challenges of moving trains across different landscapes. These machines represent the culmination of countless decisions, each made with careful consideration of how best to serve their intended purpose. And that's what makes railroad engineering so fascinating. Every design choice tells a story about the places where these machines work and the jobs they rebuilt to do.